Okay, so I touched upon this in my last video, and I didn't really get into it, but whenever you perform a regression, most of the time, the data is not perfect, right? Like you might have, let's see, turn my pen on. Okay, let's say you have something, sort of linear. It could be perfectly linear. It could be like perfectly linear in the opposite direction. It could be kind of linear, and then it could be like, it could be like, kind of quadratic, very quadratic, perfectly quadratic. You don't need to know how this happens, but the way that these regressions are calculated is by a multi-step process that people learn about in AP statistics. And it comes up with a value that indicates how good of a fit data is, how good of a fit the model is for the data that's given. In a linear regression, my handwriting is not great. Okay, in the linear regression, the value is called R. And this R is called the correlation coefficient. And your calculator will calculate it as long as you have turned on that diagnostic that I asked you to do in a previous video. If you have not yet done this, you can go to the how-to sheet to turn on the diagnostic, turn on the correlation coefficient. And basically, in a linear regression, in a modeling situation where we're coming up with an equation for a line, this R will always be a number between -1 and 1. And if R is positive, it means that the slope is positive. If R is negative, it means that the slope is negative. Okay, and the closer that R is to either 1 or -1, the more perfect it is. The more perfect the model fits the data, right? In real life, data will never be perfect, right? So maybe you'll have an R value of 0.98, 0.96, -0.96, -0.98. But the bottom line is that when we come up with this regression, we come up with this model, this R value will tell you how good of a fit that line is. Without getting into it, because we tend to not talk about it at this level, and in fact, it is in this handout incorrectly. I stole it from somewhere else. I stole it from someone who stole it from someone. It's wrong. But for polynomial fits, meaning quadratics, cubics, quartics, stuff like that, I'm just going to clear this ink right now, right? That for a quadratic regression, and we haven't done cubics or anything like that yet, but quadratics, cubics, quartics, fourth degree, stuff like that, it doesn't use R. It uses something called R squared, and it's the coefficient of determination. And R squared and R are actually not comparable. They're comparable, meaning that they aren't really calculated the same way, and we're not really supposed to compare them. But at this level, we do. Don't worry about it too much. But the same thing holds true, meaning that the closer that R squared, if your R squared is close to 1, then the fit is good, meaning that the quadratic model is a good model. So although I have this handout for you that's asking you to compare a quadratic versus a linear regression, they're not actually really comparable. I have a real problem with this. But I guess this is the level that we are teaching this at, and it is what it is. But basically, you want a number that's very close to 1. Also, keeping in mind that R squared is literally the square of something, so it's always going to be positive. But with a linear regression, I'm just going to go back for a second. Oh, I cannot go back. A linear regression, your R might be positive or it might be negative. So here is an example. I'm just going to clear all this ink off again. All right. So here we go. There is some data here about, there is a data, there we go. Here we go. The following table shows the average room rate from the years 1999 to 2001. Okay. It is asking you to create a scatter plot. I'm going to enter that data in. You're going to laugh as I go through the rest of this problem as I complain about whomever originally put the problem in this packet. It was not me, but that's okay. It's good to talk about these things. So when I put the data in there, it looks very linear. If you press zoom 9, the data looks really linear. I mean, it could be quadratic, like maybe it starts to go over, but on my test, let's just put it this way, I would never give you a problem like this where you would compare one or the other because it's just, they're so close. All right, so if you do stat, calc, and then 4 for linear regression, what it tells you is your A value is 3.6, your B value is negative 7129.06, and that your R value is 0.9, let's see, it's 0.9, I mean, we're not rounding at this point, 0.99695.997, let's go, I know that's the nearest thousandth, but that's fine, 0.997. That is a very high, right? It's very close to 1. Very close to 1. That's pretty good. The problem here with this handout, whoever got this from wherever they got it from, quadratic regressions don't come up with R values. They come up with R squared values. So if you calculate the quadratic regression, what you wind up getting, you get something quadratic. Let's say negative 0.12, and then you get your B value is 470.73, and your C value is negative 474,729.06, and your R squared value is 0.997. All right. Now it tells you what it's saying basically is that this and this are about the same, and you can use basically either. This question is ridiculous. Now, why are you making a video of a ridiculous problem? Well, it's late, and I don't have another problem to give you. This is the first time that I have taught this in this incarnation, and I'm now realizing this problem is absolutely terrible. I will fix it for the next year. But generally, when I give you something to model and ask you if it's linear or quadratic, these two things will be so far apart that one of them will be the very obvious answer, okay? Both of them indicate a very strong correlation. Correlation just means that the variables are related. Variables are strongly related. And what both R and R squared do is tell you some indication of relationship. Either way, both of those models are very strongly related. Now, because this problem is ludicrous, I don't even want to finish this problem. I just want to go to another problem that makes some kind of sense. Okay, this problem is, I'm not exactly sure where it is in the packet because I'm not looking at the packet right now, but you'll find this problem. It's in there somewhere, and if not, you can just copy it down in your notes. It's not a big deal, right? This is not that difficult. So this problem is giving you data and is asking you to find a quadratic equation that represents what is going on here, height versus distance. It's telling you around to 3 decimal places. Let's pretend for a minute it was asking linear or quadratic. It's not, right? But let's pretend, because this is how simple this is meant to be. Problem is terrible. I'm going to edit that for next year. Right? If you do a linear regression for this, right? If you do a linear regression, meaning you do stat, calc, and then 4 for linear, you get an R value of 0.608. Okay. If you do quadratic, you get an R squared value of 0.958. Right? This is what I'm talking about. This is terrible. This is bad. Okay? What we're looking for is a number close to 1, either little r or big R squared. This is a quadratic. Okay, this is very clearly a quadratic, and that is what I would give to you, right? If it were linear, you would just copy down the equation that they give you. It says y equals ax plus b, and then they give you the equation. You would use it in the exact same way, all right? But so to finish this problem, let's use the quadratic regression. In this case, the quadratic is y equals, let's see, negative 3 decimal places, 0.118 x squared. Your b value is 2.112, x, and your c value is 4.215. And then it is asking you to approximate the maximum height of the ball, right? It's asking you for the maximum. So when we find maximum, we're doing negative b over 2a. Our b value is, in this case, 2.112, and your a value is negative 0.118. And this is negative 2.112 divided by negative 0.236. Let's see, 2.112 divided by 0.236 is 8.949. 8.949. Remember that this is an x value. That's your distance. This is asking, what is the approximate height of the ball? Okay, so the height is your y value. The height is your y value. So we're going to take this x value and just plug it into the original to figure out what the y value is. And it's literally negative 0.118 x squared plus 2.112 x plus 4.215, which is about 13.665 feet, and that is your y value, which looks pretty reasonable for the data. Okay, we're going to do this problem here, this one right here, pretending that it's asking linear or quadratic. So I'm going to put the data in. Okay, and these are close. If you do a linear regression, your R is 0.973. If you do a quadratic regression, your R squared is 0.999. I'm going to say this again. In theory, we're not really allowed to compare these. So I hope the Regents, whenever it happens, doesn't ask you to compare these because they're not really allowed to do that. But let's just go with whatever is closest to 1 or to negative 1 is the one we're going to use. And really, in this problem, we don't actually have to think about it because it's telling you that it's quadratic. And it would be the same thing. So find the best fitting model for the data, round to 3 decimal places. The quadratic is y equals, your a value is 1.209 x squared. Your b value is 12.9985, which is 12.999, 12.999x. And then your c value is 504.257, 504.257. And then it's asking, so what it could ask you is, it could ask you 3 things, or at least at the moment, we could ask you 3 things. I can ask you what's happening to the population, if you know the number of years since 1970. That is one thing I could ask you. I could ask you to figure out how many years since 1970 it's been in order to get a certain number population in thousands. Not yet, because that requires a quadratic formula, which we're not ready for. I could ask you to figure out in what year do we maximize the population. I could ask you, what is the maximum population? So if I ask you anything about the maximum, you're going to use x equals negative b over 2a. If you're looking for x, you're done. If you're looking for y, you just plug it back in and get the y value. But at the moment, it's asking what will be the estimated population in 2020. You'll notice that 2020 is really far off these numbers. That's because the way that this table is set up, it's the number of years since 1970. So 2020 is what, 50 years? 50 years later? 50 years since 1970 is 2020? Yeah, that's about right. And so you're going to plug in a 50. You're not plugging in 2020, you're going to plug in 50 because x represents the number of years since 1970. I'm going to plug into y equals 1.209 x squared plus 12.999x plus 504.257. And then we're going to plug in a 50 in both of those places, and the calculator will do the rest of the work. So the estimated population should be this much at that time. In thousands. 3,726,707 thousands.